I'm going to talk about equilibrium problems. Now let's be clear what it means to say that a system is in equilibrium. A system is in equilibrium if there are no net forces and no net torques. Motionless systems are examples of systems in equilibrium. If nothing is moving in a system, there's no way that there could be a net force or a net torque. All right? We're going to use the same procedure to solve all equilibrium problems. What we're going to do is build equations that correspond to saying that the net force is 0 and the net torque is 0. Okay? Now, before we continue, there's a few basics that you need to know. Otherwise, you're not going to understand everything in the examples that I'm going to show you. Okay? So, you should know the following. You should have the following skills under your belt. Finding components of vectors. Okay? So, you should be able to do that. Finding torques. All right. I'm specifically thinking about the fact that to calculate a torque with respect to a force, you want to find the perpendicular component as well as the distance to the axis of rotation. Okay. What do I mean by the perpendicular component? If you think of the line segment from the point where the force is applied to the axis of rotation, you need to find the component of the force perpendicular to that line segment. Okay? And then you also need some basic geometry. You need to know that the angles of a triangle add up to 180. All right? And you need to know some things about parallel lines cut by a transversal. Let me do an example that shows you the skills that you need. Okay? Let's calculate the torque due to the normal force of the wall on a ladder resting against that wall. Let me draw a corresponding picture and then we'll continue. Okay, so here's a picture of a ladder resting against a wall, making an angle with a measure of theta with respect to the ground. Okay, and the ladder has a length L. Now, just to give some numbers to this example, let's say that the normal force has a magnitude of 50 newtons. Let's say that the length of the ladder is 5 meters, and let's say that theta is 30 degrees. Okay? So here is how I would calculate the torque due to the normal force of the wall acting on the ladder with respect to the axis of rotation being the point where the ladder makes contact with the ground. Now let's be clear, the force that I've drawn is not the only force acting upon the ladder. There's gravity, there's the normal force from the ground, there's the friction with respect to the ground, there might be friction with respect to the wall. So for an equilibrium problem, you would have to find the torque contributions from all those forces. All right, but I just want to show you the flavor of how equilibrium problems are with this with this one example first. Okay, so to calculate the torque, I would use the general formula, okay, that I've just written there. R is the distance of the point of contact of the force that you're trying to find the torque for. The distance from that point to the axis of rotation. So for this problem, R would be the length of the ladder, L. Okay, and we want to find the component of the normal force perpendicular to the ladder. Right? All right, so here's how I would do it. So there is a right triangle formed with respect to the wall, the ground, and the ladder. And one of the angles of that triangle has a measure theta. The other acute angle has a measure 90 degrees minus theta. That will be useful. If I extend the vector, in other words, if I draw the line that the vector is on, okay, I can calculate the angle between that line and the ladder. That angle is theta. You should be able to determine that. Okay, let me show you two ways that you can see that the angle between the ladder and that purple line must have a measure theta. So if you know about alternate interior angles with respect to two parallel lines cut by a transversal, okay, that's one way to see that that angle has to have a measure theta. Another way to see it is that the angle on both sides of the ladder, the one angle has a measure of 90 degrees minus theta, so that other angle with respect to the purple line, both of those add up to a right angle. Okay, that's the second way to see that that angle has to have a measure theta there between the ladder and the purple line. Okay, so all of that is to say that you should be able to now see that the component of the normal force perpendicular to the ladder is n sine theta. All right? The triangle that you can use to calculate that, the right triangle, is this one. You can move the normal force vector over to be the hypotenuse of that right triangle. Okay? Let me show you another way that you can calculate the component of the normal force perpendicular to the ladder. Let's draw this green line that is perpendicular to the ladder and goes through the point of contact. Okay, so using your geometry skills, you should be able to determine that the angle between the green and purple line has a measure of 90 degrees minus theta. Okay, so if you move the normal force over and think about the following right triangle. So if you make the normal force be the hypotenuse of that right triangle, then you can see that the component of the normal force perpendicular to the ladder is n cosine of 90 degrees minus theta. Okay? Putting it all together, we get that the torque is n sine theta times L. So 50 times the sine of 30 degrees times 5. All right? That gives 25 times 5, or 125 Newton meters. Okay? It's very important that you understand all the steps that I just did. Okay? Notice again that I used some basic geometry. I had to use my understanding of vector components, and then I had to use my understanding of the torque formula. All right? If you don't understand everything in this example, again, you're not going to understand the the next equilibrium problems that I'm going to do. Okay, you're just going to get frustrated, and I don't want you to get frustrated. So understand this before you continue with this video. All right, now let's continue and do some other equilibrium-related problems. The next problem involves hanging masses. Give me a minute to draw a picture. All right, almost done. All right, so this picture, first of all, it contains a horizontal meter stick. That's what the brown rectangle represents. And there's two weights hanging from that horizontal meter stick. That's what the purple rectangles represent. There's a cable suspending the meter stick from a ceiling. That's what the black vertical line segment above the meter stick represents. All right. Now the distance of the point of contact of the cable above the meter stick, the point of contact with the meter stick, the distance from the left side is denoted by x. All right, and x is equal to 0.4 meters. The distance of the point of contact of the cable suspending one of the hanging masses from the distance of the point of contact of that cable with the meter stick, the distance from the left side is denoted by A, and A is equal to 0.1 meters. And then the corresponding distance for the other hanging mass is denoted by B, and B is equal to 0.6 meters. The length of the meter stick is denoted by L, which is 1 meter. Okay? One of the hanging masses, the one that corresponds to the variable, the distance A, that one has a mass m sub A, denoted by m sub A, which is equal to 0.2 kilograms. And the other hanging object has a mass m sub B, but we don't know what that is. We're not given that. Okay? And the mass of the ruler is, let's assume it's negligible compared to the masses of the hanging masses. So I'm going to write 0 kilograms. Now, of course, it's not exactly 0, but just assume it's a really small number that we can essentially treat as being 0. Okay? So, for this question, I'd like you to try to calculate the tension in the cable suspending the meter stick from the ceiling, and the m sub B, the mass of one of the hanging masses. Okay? So pause the video now and try to find the values of those two variables. All right, so I'll go ahead and show you how I would do it now. So first I'm going to identify all the forces acting on the horizontal meter stick. So there's a tension due to the cable with respect to the ceiling, there's a tension equal to the weight. There's two of those due to one for each of the hanging masses. And then there's also the weight of the meter stick, but that, as I said, that's the mass of the meter stick is approximately 0, so that's going to be 0. So 0 newtons for the weight of the meter stick. The tension due to the mass m sub a, the object with the mass m sub a, that has a weight m sub a g. The other object has a weight m sub b g, and then the tension in the cable with respect to the ceiling is T. All right, so there is no net horizontal or vertical force acting upon the meter stick. Okay, therefore the tension has to exactly balance the weight of the two hanging masses. So T equals m sub a g plus m sub b g. All right. Now let's calculate the torque, at the net torque on the meter stick. And I'm going to choose for the axis of rotation the point where the cable with respect to the ceiling makes contact with the meter. I'm going to select clockwise torques to be positive and counterclockwise torques to be negative. So the torque contribution due to the hanging weight with a mass m sub b is m sub b times g, and then for the distance I need to use b minus x, and then the weight due to the ruler doesn't contribute any torque. The tension due to the cable with respect to the ceiling doesn't contribute any torque because the distance to the axis of rotation is 0. And now I'm going to subtract the torque contribution from the other hanging mass, which is m sub a g times x minus a. Okay, so that equals the net torque, so that's equal to 0. And now let's simplify this expression, this equation. So we can ignore the zeros. Let's divide the rest by g, and we are solving for m sub b. So let me move the term that includes m sub a to the other side. So m sub b is equal to m sub x times x minus a all over b minus x. M sub a is equal to 0.2. X minus a is equal to 0.3. B minus x is equal to 0.2. Notice that the 0.2 in the numerator and denominator cancel. So the mystery mass, m sub b, is equal to 0.3 kilograms. Okay? Now we can calculate the tension in the cable with respect to the ceiling using that value. So m sub a is 0.2 times 9.8 plus 0.3 times 9.8. That gives 0.5 times 9.8, half of 9.8, which gives 4.9 newtons. Okay, so let me reiterate that you have to be careful to denote either clockwise or counterclockwise torques to be positive, all right, and then whatever you decide, the other direction will be the negative torque contributions. Okay. let's do a problem now involving a hanging sign. Give me a minute to draw a picture. Okay, almost done. All right, so what the picture represents is a horizontal pole. That's what the blue rectangle corresponds to, connected to the side of a building, to a vertical wall, in other words. And there's two cables fastened to that pole. One of them is holding up a sign. That's what the purple rectangle represents. And the other cable above the one above is above the pole. That's what the purple line segment represents, and that's to keep the pole horizontal. All right. The length of the pole is denoted by L, and L is equal to 2 meters. The distance of the point of contact of the cable holding up the sign to the pole from the wall is denoted by X, and X is equal to 1.5 meters. The angle that the cable above the pole makes with the horizontal pole, theta, that's equal to 30 degrees. So the angle has a measure of 30 degrees, in other words. The weight of the sign is denoted by W sub S, and that's equal to 30 newtons. And the weight of the pole is 40 newtons. All right, so in this problem, the question, the puzzle, whatever you want to call it, is to figure out what is the tension in the cable above the pole. Okay, so pause the video if you like and try to figure out the magnitude of the tension force on the pole. All right, do that now, please. All right, I'll go ahead and show you how I would work this one out. So first, I would identify all the forces acting on the blue horizontal pole. So we've got the weight of the pole. We've got the force due to the weight of the sign. We've got the force due to the cable above the pole. And then due to the wall, we've got a horizontal and a vertical force. The horizontal force is the normal force. The vertical force might be due to friction. It might be a combination of friction and other contributions. Okay, so we have the weight of the pole, so let me write WP next to the vector with respect to the center of the pole, and then the weight of the sign, and then the tension. All right, so those are all the forces. Those red vectors, those red arrows denote all the forces acting on the blue horizontal pole. And if we wanted to calculate the force of friction due to the wall, that force, we might use an equation that says that there's no vertical net force on the pole. All right, but the question only wanted the tension, and you're going to see that simply insisting that the net torque is 0 is sufficient to calculate that. So I'm going to choose my axis of rotation to be aligned through the point where the pole touches the wall. All right, and so that's going to allow me to ignore the forces due to the wall, the normal force and the force of friction or whatever else is causing a vertical force. All right, so let's now sum up the torque contributions on the pole. And I'll decide to call clockwise torque contributions positive and counterclockwise torque contributions negative. So due to the weight of the pole, so that'll be WP multiplied by half the length of the pole, so L over 2. And now let's add the contribution due to the weight of the sign. The distance of the point of contact of the cable holding up the sign from the wall is X. And so now we just have to subtract the contribution from the tension. And we're going to use the perpendicular component, the component perpendicular to the horizontal pole. So T sine theta. And we'll multiply that by L. And that is equal to 0, right? Now we can move terms around to isolate T, and we get the following expression. T is equal to WP times L over 2 plus WS times X divided by L sine theta. All right, so that's equal to, let's see, 40 times 1 plus 30 times 1.5 divided by L sine 30. L sine 30 is equal to what? Hold on, let me finish writing the numerator. 2 times, and then the sine of 30 is 1/2. So the denominator is unnecessary. We can ignore it. And on top, let's see, 30 times 1.5 is 45 plus 40. That gives 85 newtons for our answer. Okay, so for this problem, again, remember that we need to be careful about the signs of our torque contributions. Also, notice that the choice of the axis of rotation allows you to completely ignore certain force vectors. All right, now let's try another problem. For this next problem, there will be a crate resting on a ramp, and the ramp will be leaning against a smooth wall. So let me draw a picture of what I'm talking about. All right, so This picture denotes a crate. That's what the purple rectangle represents. And the crate is resting on a ramp. That's what the blue line segment represents. The ramp makes an angle with respect to the ground with a measure of theta. The crate is a distance c from the point where the ramp touches the ground. Okay? The weight of the ramp is 30 newtons. The weight of the crate is 20 newtons. I'm denoting the weight of the ramp by W sub r, the weight of the crate by W sub c. The distance of the crate from the point of contact of the ramp with the ground, that was c. C is equal to the 1/4 the length of the ramp. The length of the ramp is L. All right, and the angle, measure theta, the measure of the angle between the ramp and the ground, that the theta is equal to 30 degrees. And so the puzzle for this one, the question is to determine the normal force of the wall on the ramp. So I'm going to call that N sub W. And also to determine the frictional force of the ground on the ramp, I'll call that F sub FRIC. All right, so given this information and using the picture, can you determine the magnitudes of those two forces? So go ahead and pause the video and take a shot at that if you like. All right, so I'll go ahead and work this out myself. So first I'm going to identify all the forces on the ramp. So there's the weight of the ramp, and I'll denote that as a force applied at the center of the ramp. There's a force due to the weight of the crate. There's the normal force due to the wall. And the wall is smooth, so there's no frictional force due to the wall. There's a normal force due to the ground, and then there's the frictional force due to the ground. All right, let me give a name to all those forces. So N sub W, W sub R, W sub C, normal force of the ground, and force of friction. Now, we weren't asked to find the normal force due to the ground, but can you see that that has to equal the weight of the ramp plus the weight of the crate? Because there can't be a net vertical force. So the normal force of the ground has to be 50 newtons, but that wasn't what we were asked. Notice that the normal force, the magnitude of the normal force due to the wall has to equal the frictional force due to the ground. All right, that's because there can't be a net horizontal force on the ramp, right? So once we can find the magnitude of either one of those forces, we automatically have the magnitude of the other one. All right, so now let's make an equation denoting the fact that the net torque on the ramp is 0. And I'm going to work with the axis of rotation with respect to the point where the ramp touches the ground. Okay? And so, let's define, let's say, counterclockwise torques to be positive and clockwise torques to be negative. All right, so we've got the contribution due to the weight of the crate, and we have to find the perpendicular component, so that's going to take some care. Let's do some geometry analysis. So let me draw a line perpendicular to the ramp, and let's see if we could figure out the measures of some angles. So we have a triangle, there's a right triangle with the angle having a measure theta, and this angle right there has a measure of 90 degrees minus theta, because all the angles of a right triangle add up to 180. And also, can you see that if I could draw a line through the point of contact of the vector, let's see, like this, can you see that there is also an angle with a measure theta, 90 degrees minus theta? So that's an example of exterior angles with respect to two parallel lines. So there we have two angles with a measure of 90 degrees minus theta, and so therefore this angle right there, that one has a measure of theta, because there's that angle plus the other angle I was just focusing on, both of those angles add up to a right angle. So all of that is to say that the torque due to the weight of the crate is WC cosine of theta times C. All right, and then for the weight of the ramp, it'll be WR cosine of theta times L over 2. And then I'm going to subtract the contribution due to the normal from the wall. And so that will have a distance L, but now I have to do some more geometric analysis before I can get the perpendicular component. So let's draw some lines. And so we've got this angle has to be 90 degrees minus theta, because the ramp is the hypotenuse of a huge right triangle with the acute angles having measures theta and 90 degrees minus theta. Therefore this is theta, this is 90 degrees minus theta, and therefore the normal force, the perpendicular component of n sub w is n sub w times the cosine of 90 degrees minus theta, or the sine of theta, times L, and that whole expression equals 0. Okay, now we can simplify. So the L's cancel, and the C is equal to L over 4. So I can cancel that and put a 1/4 in its place. Okay, and the goal is to solve for the n sub w. So I can also divide everything by the sine of theta, and cosine of theta divided by the sine of theta, that's 1 over the tangent of theta, or if you like, the cotangent of theta. Okay, now let me move n sub w to the other side of the equation, and let me write what that'll give me on the bottom right of the board. So n sub w is equal to w sub c times the cotangent of theta all over 4 plus w sub r times the cotangent of theta all over 2. Now let's plug in numbers. So w sub c is 20. 20 over 4 is 5. So 5 times the cotangent of 30 degrees. W sub r is 30. 30 over 2 is 15. 15 times the cotangent of 30 degrees. All right, so the cotangent of 30 degrees is the cosine of 30 degrees over the sine of 30 degrees, which is root 3 over 2 over 1/2. So the cotangent of 30 degrees is root 3. So 5 root 3 plus 15 root 3 gives 20 root 3. You can punch that into your calculator and see that the normal force due to the wall is 35 newtons. All right. Furthermore, the friction due to the ground has the same magnitude, therefore it is also equal to 35 newtons.